that, I will turn it over to Dr. Jones.
Great. Thanks so much, Kim. I appreciate it. I'm recording this presentation. If you lose internet or want to watch more of it later, all of these will be on my YouTube channel, and there's a link to that on my webpage. So yeah, thanks again, Kim, for co-hosting. If you do have any questions tonight, this is our smallest group. There's 22 of you. Just interrupt. I want to make sure I get your questions answered. And if you have questions after tonight, give me a call at 994-6076 or send me an email anytime. So tonight I'm going to cover cover crop management, how to benefit the subsequent crop, how to benefit soil health. So today's goals are to present cover crop management considerations, discuss cover crop effects on, as I mentioned, the following: cash crop yield, protein, and profit, as well as cover crop effects on soil quality parameters, including soil organic matter and nitrogen availability. And finally, I'll answer the question, does cover crop diversity matter? So there's been quite a bit of focus in the last about, I'd say, 8 years on cover crop cocktails. Are they any better than single cover crops? So as most of you know, there's a lot of challenges with summer fallow. There's some pros. Summer fallow helps recharge moisture, provides a nitrogen benefit, and produces more consistent yields. There's some negatives too, such as loss of soil organic matter, increased erosion, saline seeps and nitrogen leaching, and decreased soil health or soil quality. So what are some alternatives? Well, no-till is certainly an alternative. No-till by itself will conserve some water and also protect the soil. And then there's also the option of cover crops. So what we call a partial fallow replacement. We're not growing cover crops for the entire summer fallow period, or we'd use up all the water we were trying to save, but it's a partial fallow replacement. So typically, at least in our studies, we plant in early May and we terminate in early July. There's some people who plant fall cover crops, some who plant a little earlier and let them go a little bit later. So my colleague Perry Miller has been conducting cover crop research at MSU since 1999, and he has generally found higher grain yields and or protein after cover crops when he seeds winter legumes, meaning compared to planting spring legumes. He seeds spring covers early versus late, terminates early, so around first bloom, somewhere when there's one bloom per plant, versus letting them go a little later, say towards pod, and tilling the covers versus spraying them out. So why is that? Well, winter legumes do fix more nitrogen. They get an earlier start in the fall. They're growing like crazy when spring covers might be planted, and they do tend to fix substantially more nitrogen. Also, there's more time for the soil water to be recharged and nitrogen to become released from residue if you seed early and you terminate early. And finally, by tilling covers, there's a faster nitrogen release and fewer end losses. We know there's disadvantages to tillage, but at least in our cover crop research where we've compared till to no-till, it does seem like there's a little advantage of tilling those covers in. So Perry's Montana studies have confirmed some earlier Saskatchewan studies that really showed how important that termination timing is, especially when water is limited. So this is some work he did in about 2005 at 3 locations: Denton, Havre, and Amsterdam. Denton, nitrogen and water, neither was limiting that year. Disease, it turned out, was limiting at Denton. In Havre, water was limiting, nitrogen wasn't. And at Amsterdam, nitrogen was limiting and not water. So kind of without even planning, he found some really unique, interesting characteristics at each site. And then he tracked grain yield in bushels per acre following these cover crops. The brown bars are chem fallow as a control. The green bars are a cover crop terminated at early bloom, and the yellow bars are a cover crop allowed to go all the way to mature pod. So when neither nitrogen nor water was limiting, as you might expect, there was really no difference in yield among those three different treatments. But when water was limiting and not nitrogen, chem fallow produced about 5 more bushels per acre than a cover crop terminated early, which produced about 10 more bushels per acre than a cover crop terminated late. So this study here done at Harvard really emphasizes how important it is if you grow covers to terminate early, to not use too much water. At Amsterdam, where nitrogen was limiting and water wasn't, then the early terminated cover crop actually outperformed both chem fallow and the cover terminated at pod. So water didn't really make a difference. This cover crop probably provided a little bit of nitrogen because Perry was primarily studying peas as a cover crop, and therefore it produced the highest yield. So in summary, from this study, haying covers at early bloom produced higher spring wheat yields the following year than harvesting pea when either water or nitrogen was limiting. So this is a summary, a really amazing summary that Catherine put together for me from a wide range of studies conducted in Montana and one conducted in Saskatchewan. What we're showing here is spring soil water, where a negative number means that the cover crop ended up with less spring water than fallow. So that's probably going to be expected, right? There's going to be very few situations where following a cover crop, there's going to be more water because covers use water. On this vertical axis is plotted wheat grain yield, and again, cover minus fallow. So 0 would mean there was no difference in yield following cover or fallow. A positive number would mean that cover crops actually helped with yield, and a negative number would indicate that covers decreased yield. So first notice there's only one point over here where covers actually increased water. So that might be a year when there was a lot of precipitation, maybe that residue held in a little more water. But for the most part, covers are going to use up water and decrease yield. There are a few cases where covers actually increased yield. So that again may be where water's not limiting, but nitrogen is limiting. So for the most part, if we kind of look where most of these dots are, there's about, a 1 to 2 inch decline in using covers in soil water, and about, somewhere between 2 and maybe 8 bushel per acre yield hit. There are some really large yield hits, and there's also some where the covers actually helped yield. So again, anything less than this line, less than 0, means the cover ended up with less water and lower yield than fallow. Anything over here, the cover increased water, and everything up here, the cover had less water, but higher yield than fallow. Probably a wet growing season made up for that lack of early spring water. So looking at a long-term study, and for those of you who have logged on before, I've shown some results from this study. This is this long-term study that Perry's been running since 2002, where we looked at the long-term effects of no-till pea grown for grain, forage, or a cover crop, and we compared that to a fallow wheat system. This is a wetter area than most cropped land in Montana, so about a 16-inch rainfall zone, 16.3, Perry tells me, to be more explicit. So I was just looking at all of the info in the chat. Our pea was terminated at full pod, even though we recommend terminate a little bit earlier. We thought we could get away with a little bit later with that increased amount of growing season precipitation. And then we had two different nitrogen rates, a full rate, meaning 3 pounds of available nitrogen per bushel, and half that rate. So what do we find? I'm going to start looking at grain yield. Here we have these 4 systems out of the 9 that were in this study that I want to focus on tonight. No-till fallow, pea grown for grain followed by wheat, pea grown for hay followed by wheat, and pea grown as a cover crop followed by wheat. And here what I'm plotting is winter wheat grain yield in the 14th year. So this was in 2016, which was a very good growing season. You can see that we were growing 70 to 90 bushels. And I plot this for both the full nitrogen rate and the half nitrogen rate. So in every case, the full nitrogen rate somewhat exceeded the half nitrogen rate. Notice that no-till fallow had the highest wheat grain yield. The pea grown for grain and the pea grown for hay had lower yields, and the pea cover had essentially intermediate yield. So not too much worse than no-till fallow. When we look at protein, the no-till fallow did not do very good. So protein was substantially less following fallow than following pea grown for grain, hay, or a cover crop, especially at that full nitrogen rate. At the half nitrogen rate, it's a little less dramatic. This is another amazing graph that Catherine put together for me, focused on a large number of studies in Montana and 1 in Saskatchewan, 47 site years of data, looking at the number of site years of that 47 at which grain protein was decreased following a cover crop versus increased. So these numbers indicate that the protein was increased by 1 percentage point, 2 percentage points, 3 percentage points. So for the most part, growing a cover increases grain protein. Only in a few cases did growing a cover decrease grain protein compared to fallow, and in about 10 of those 47 cases, growing a cover didn't affect protein compared to fallow. So for the most part, covers are good at increasing protein. Most of these were studies using pulse crops as the cover crop, either pea or lentil, and so they likely provided a little more nitrogen, probably also used a little more water, so yield was less, and therefore more of that nitrogen was concentrated in the grain than when you grow a lot of yield following fallow. Any questions so far? And those of you who are on Catherine's email list should have gotten all the links that she sent in the chat. But for those of you who either didn't receive that or or didn't receive that, all of those are over there as links. Question from Tim is, were all the protein studies done using the same mix of crops? No, so those were done by a variety of researchers, not not collaborating. Most of those were sole species pea, and some were sole species lentil. Of those, I don't think any. Let me look back. Houseman would have been mixed cover crops, so up to 8 species, and I'll show some of that work later. Allen was lentil, Burgess was lentil or pea, Miller et al. This was pea, O'Day was pea or lentil, and Tallman was mixed cover crops, and Zettner was lentil from memory. So it was a real mix, and maybe a better chance that protein wouldn't go up if it was a cover crop that had no legumes in it. So a really good question. Other questions? All right, well, I'm going to move on then, and always feel free to type up a question or unmute yourself with so few people out there if you don't feel like typing. So again, focused on that long-term study west of Bozeman. This is looking at the 4-year average net return in dollars per acre for pea green manure, a cover crop, followed by wheat, versus fallow, followed by wheat, at both the full nitrogen rate and the half nitrogen rate. There's very few studies where cover crops can compete with other systems because seed is pretty expensive and there's no net revenue when a cover crop is grown unless it's grazed. So this was pretty interesting that there was no difference in profit between a pea green manure and a fallow system at the full N rate. And actually at the half N rate, the pea green manure followed by wheat somewhat outperformed the fallow wheat, not significantly, but numerically. However, so that was in 2009 to 2012, which were pretty wet years at the post farm. When we turn to a drier period and look at those same four treatments, again, the dollars per acre sum from 2013 to 2016 for four different scenarios. So the full N rate at a high discount, protein discount, and a low protein discount, and then the half N rate at both the low discount and the high discount. What really stands out is the pea grown for grain followed by wheat, regardless of the system, produce far more profit than no-till fallow, pea grown for hay, or the pea cover crop. So in a dry years, cover crop just really can't compete, especially with a pea that's grown for grain and therefore produce some profit in that year. So some take-home messages from that 14-year plot study is that wheat grain yield and protein benefits take time. We really didn't see very big differences in the first 6 years of the study. We started seeing larger differences after that. We had a few cover crop cycles in high moisture years and a few cover crop cycles with dry years. We found that economic returns were more stable with the cover crop, meaning less dependent on nitrogen rate because they were providing nitrogen, but also the profits were much higher with pea grown for grain than a cover crop. So a question might be, well, how do results compare in locations outside the Gallatin Valley, which is blessed with a little more rain than the rest of the state? So here I'm looking at a study done in Moccasin, which doesn't have a lot less rain than we have, but they certainly have shallow soil, so not a very good ability to hold moisture. What we're showing here on the horizontal axis is the amount of fertilizer applied from 0 up to about 120 pounds of nitrogen per acre, and wheat grain yield following either a lentil green manure in green or a lentil grown for grain in yellow. So notice that the lentil grown for a green manure or cover crop, the wheat following that produced about 5 to maybe 7 bushels per acre more simply because that cover crop would have used less water. It would have been terminated earlier than letting lentil grow all the way for grain. Protein, as nitrogen rate increased, protein increased. And again, for every nitrogen rate applied, the protein was higher following that cover crop than following the lentil grown for grain. But when we look at net return, in dollars per acre, that lentil grown for grain followed by wheat always produced more net return in dollars per acre than the green manure or the cover crop. Again, there's no revenue in that sprayed out cover crop year, and there's substantial revenue in the lentil year. So take-home message there in short to long-term studies in different regions in Montana, pulse wheat returns more profit than a pulse cover crop wheat, at least when that cover crop is sprayed out. Any questions on anything I've covered so far? And some of you might be thinking, well, he's pretty anti-cover crop. He's pointing out these negatives, but yield, protein, profit aren't the main reasons that a lot of people are growing cover crops, which is actually for soil health reasons, which I'll get into shortly. Okay, again, I'll keep watching the chat box. So soil quality and soil health, you've probably noticed, are used somewhat interchangeably. I've seen some people differentiate them, and I kind of like this differentiation. And so soil quality, at least by some, is defined the properties that change little, the quality of the soil, and maybe don't change much at all with land use practices. So things like texture, pH typically doesn't change very much, cation exchange capacity, whereas soil health are more dynamic properties that may be sometimes subjective to measure, but can change more with land management. So things like aggregation and microbial activity, tilth, nutrient availability, water holding capacity, and compaction. Soil organic nitrogen and soil organic matter are often seen on both lists. They're quality of the soil, but they can be changed. And then just kind of a thought question for you is which is more likely to be influenced by cover crops? And I'll show some data on that, but I would say for the most part, probably soil health. It's hard to change texture, almost impossible. Hard to change pH with cover crops. Cation exchange capacity is tied to texture, so almost impossible to change with cover crops, whereas all of these can be changed with covers. One thing that covers change is temperature. So this is work that Perry Miller and I did several years ago, looking at temperature 2 inches down in the soil, both before cover crops were terminated and then after cover crops were terminated. Here on the vertical axis, we measured temperature in degrees Fahrenheit, and we did that for fallow in yellow, pea in green, and full in a red triangle. So notice that early in the growing season, before cover crops had really established, there was really no change. And then somewhere in late June, the covers must have started growing and started shading the soil. And by the time those covers were terminated on July 5th, the temperature difference ranged from, 66 up to about 78, so about a 12-degree difference. And notice that even after termination, that difference stayed about the same for about 3 weeks as those crops probably slowly died and senesced. And that change continued for at least 2 months after termination. Now, we don't know exactly what these fairly large temperature differences will do up to about 12 or 15 degrees, but certainly microbes, soil microbes do not like to be close to 100 degrees. They do not do very well at that temperature. So possibly microbes were killed in those upper soil horizons. There might be other disadvantages of these high temperatures. Certainly evaporation would be one big problem with higher temperatures. Something else that covers can affect would be soil organisms. Here I plot organisms in grams per dry soil on the vertical axis for both fungi in purple and bacteria in light blue for a fallow system, followed by wheat, continuous wheat, a lentil, flat pea, vetch, and pea, all in rotation with wheat. Notice how much more fungi and how much more bacteria there were under these legume cover crops compared to more traditional fallow wheat and wheat systems. And this was following 6 years of rotation, but still some pretty dramatic differences. Infiltration rate can also change due to cover crops. So again, jumping back to the study west of Bozeman, this was infiltration that rates that Catherine and a graduate student, Willa, mentioned measured in fall in our long-term rotation study. Here we have infiltration rate in inches per minute. So this is how fast can water move through the soil in inches per minute. For tilled fallow, no-till fallow, continuous wheat, pea grown for grain, pea grown for hay, pea as a cover crop, and then a system that was conservation reserve program for 10 years, followed by a pea grain wheat system for the last 8 years. These are dramatic differences. In the only other study where I measured infiltration rates, I could not really detect differences after a 7-year cover crop study, but maybe because this was after 18 years of different cropping systems, we found that these recrop systems had 7-fold the infiltration rate of these ballast systems. So that means that water will move below the surface, have less of a chance of running off, and also have less of a chance of evaporating because that water's down in the root zone rather than sitting at the surface. Notice that the pea cover crop did as well as any system numerically, was the highest infiltration rate of any of these systems, and certainly statistically higher than either fallow system. Enzyme activity also is affected by cover crops and cropping systems in general. So again, those same 7 rotations, looking at what's called the geometric mean, or the average of 5 different enzyme activities. These are enzymes that microbes emit into the soil to help them use nitrogen or carbon or phosphorus more easily. And so here again, the pea cover crop did as well as any of these recrop systems. It's pretty much about the highest and did significantly higher than the tilled fallow system. And finally, in that same study, here I'm plotting soil organic matter in tons per acre. The red line was the soil organic matter at the beginning of the study in 2002. And the full nitrogen rates are all shown on the left, and the half nitrogen rates on the right. The pea cover here didn't, really do that much better than any system. It had about the same soil organic matter as in 2002. Maybe it's because it was a legume cover crop, which produces a lot of nitrogen. Maybe it broke down faster, but it seems, at least in this system, that the best way, if you want to increase soil organic matter, is to actually grow a perennial crop, a conservation reserve program crop. Richard, could you mute your microphone, please? Actually, I got it for you. So again, cover crops don't seem to increase soil organic matter much more than other systems, at least in this study. So legume cover crops are great at releasing nitrogen, and cover crops residue releases nitrogen more quickly than what's left over after harvesting a legume grain. Based on this work out of Oregon, we feel that legumes should be at least 40% of the cover crop mixture, and I'll show you why. So this is a study where they looked at different plant growth stages for 4 different cover crops: 100% legume, 75% legume, 25% legume, and 100% cereal. Then they measured plant available nitrogen from the cover crop. Anything above this line would be contributing to the plant available nitrogen. Anything below this line would be depleting plant available nitrogen. So notice 100% legume, as it goes through the vegetative stage to the bud stage, produces a lot of available nitrogen. The cover that was 75% legume produced somewhat less, when it was only 25% legume and terminated somewhere around say the boot stage or the bud stage in a legume. Notice there was really no benefit. And a cereal cover crop had a slight benefit early in the growing season, but by boot, it actually tied up nitrogen. Cereals and grasses have what's called a high carbon to nitrogen ratio that ties up nitrogen. Legumes have a low carbon to nitrogen ratio, which provides nitrogen. So again, probably should have up in this range at least 40%, maybe at least 50% to really provide nitrogen to the next crop. This is also work done at Oregon State University, where they wanted to see if there was a relationship between total nitrogen in the residue. here on the horizontal axis, total nitrogen as percent, and plant available nitrogen expressed in pounds of nitrogen per ton of residue. And what they found was that at low total nitrogen in the residue, there was really no advantage to plant available nitrogen. It simply did not go up, whether we are at 4 weeks after mixing that into the soil or 10 weeks. So you might be saying, well, what do these numbers mean and what type of residue have those numbers? Well, immature legumes, so legume terminated before maturity, has pretty high nitrogen, somewhere around 3 to maybe 4%. Cereals and brassicas at flower maybe have closer to 2%, and cereals post-heading, so pretty late in the growing season, might have only, say, about 1% nitrogen. So again, if you want a nitrogen kick from your cover, you really want to be growing legumes and terminating them fairly early. This is work done by our neighbors to the north in Alberta. And what it really shows is that nitrogen isn't just released in the next growing season after a cover crop, but it can be released for 2 or maybe even 3 years. So here I have weeks. Here I have weeks on the x-axis going up to 160 weeks, so 3 years, and the amount of nitrogen released in pounds per acre over that time. Starting at the bottom, P that's grown for grain, so all the residue that's left doesn't have a very high amount of nitrogen. Most of the nitrogen leaves in the harvested grain. But notice that the nitrogen released continues to go up even after 60 weeks, 100 weeks, and maybe starts plateauing somewhere around 2 years. Faba bean, grown for grain, starts a little bit higher, a big kick right at the beginning, but again, nitrogen release continues for a couple years. Vetch grown for cover really increases a lot of nitrogen in just a few weeks, but then continues to provide nitrogen to the soil. And a faba being grown for cover has a lot of nitrogen released in the first 5 or 6 weeks, but that nitrogen continues to get released all the way till 3 years after being grown. So you might see a benefit for more than just the next growing season. If you do want to maximize that nitrogen benefit, you really probably want to take practices, implement practices that increase nitrogen fixation. So that means good inoculation with a rhizobia inoculant. And then in certain soils, sulfur deficient soils, you're going to want to fertilize with sulfur. So this is work that I and my graduate student Caleb did this year at the post farm, where we measured nitrogen fixed in pounds per acre for 8 different lentil treatments. 5 of those treatments had no sulfur. 3 of those treatments had sulfur. And notice that in every case where sulfur was added, and not very much, just 5 pounds of nitrogen per acre, the amount of nitrogen fixed went up by about 30 pounds per acre. Some of that ended up in that crop, and a lot of it ended up for the next crop. A lot of it ended up as residue. Any questions so far on anything that I've covered? Great question. Why has pea hay underperformed in most of the studies? So when pea is hayed, that means that most of the above ground biomass is removed. I was surprised it was, say no better than pea grown for grain, where a lot of the nitrogen is removed, but when the pea seed is removed, it's still leaving a lot of carbon behind. And so all those leaves and stems get left, whereas haying, most of that leaves. And so I think it's that a lot more of the residue was being removed than, say, for a cover crop or a perennial crop like a CRP or pea grown for grain or even wheat on wheat, where a lot of stubble is left after a wheat crop. So I think it's just that more of the residue was being removed. That's just a guess, and I was a little surprised how it didn't perform maybe a little more similarly to some of the other treatments. Good question. Other questions? All right. Can you also review termination techniques, chemical versus tillage? So, um, so chemical would be some sort of herbicide. Glyphosate is used somewhat frequently. One downside of glyphosate is it kind of produces a slow kill, and so other people have used chemicals that burn things down faster. Some of those might be as or more toxic than glyphosate. So it's hard to know what chemicals to use, but basically the crop is sprayed. So that's what chemical tillage means. Um, for mechanical, there would be, light disking, something that basically kills the crop but doesn't mix it in very well. Or there would be deeper plowing, duck foots. There'd be different ways of getting that residue down into the soil. And then something that's more experimental, not that used that much on commercial farms, is something called crimping. And so crimping would be crimping the plant at the base with basically a big roller that has kind of sharp metal spines on it that crimp the plant, prevent water from continuing to be taken up, but leaves that residue on the surface. So kind of could be seen as the best of both worlds. No chemical is used, but also no possibly, soil degrading tillage would be used. We've experimented a little bit with it. Works pretty good on peas, not so good on something like sweet clover. All right, great questions. So on to some mixed cover crops. The big question that Perry and I and Kathy Zabinski asked back 8 years ago was, does increased crop diversity, cover crop diversity, improve soil health? And we measured a number of biological and chemical and physical properties. The ones that I'll focus on tonight are soil enzyme activity, potentially mineralizable nitrogen, so how much nitrogen gets released by microbes, and soil organic matter. And then does increased diversity increase subsequent grain yield and protein? So this study involved nitrogen fixers. We had 4 different what we called functional groups, where we grew spring pea and lentil. We had fibrous rooted species such as oats and millet. We had tap rooted to try to break up compacted layers. And we also had brassicas, which tend to, have a lot of rapid ground cover, produce quite a bit of biomass, and might control disease in certain cases. As our first, what we call the big 3, we had a summer fallow control treatment, a sole species pea, and then an 8 species CCM or cover crop mixture. We also had 4 2 species mixes and fixers, fibrous root, taproot, and brassica, and then 4 6 species mixtures where we basically took that full cover crop mixture and then subtracted out a functional group. So did that one matter or not? Did it matter if we pulled out nitrogen fixers? Did it matter if we pull out the fibrous roots? One thing we learned in the first few years of the study was, of course, moisture matters. We only grew 0.2 tons per acre at Conrad, 0.4 tons per acre at Amsterdam in that drought year 2012, which affected all of Montana. 2014 was a lot better year. We grew a ton per acre at Conrad and 1.4 tons per acre at Amsterdam. One thing that we've noticed or learned in this last year of the study, when we came back and soil sampled in 2019 after 7 years, 4 cover crop cycles, and then 3 wheat cycles, was that soil organic matter seems fairly strongly related to the amount of biomass that we return to that soil. And you might be saying, well, duh, why wouldn't it? But we didn't really know before we did this study. We knew that some covers might break down more quickly, others might stick around more. So we weren't sure that we would actually find that. That was at Conrad. At Amsterdam, we found a really strong relationship. In fact, if we threw up as one outlier, it would be an amazingly strong relationship between biomass returned and soil organic matter. And then another surprise was that nitrogen rate did not affect the soil organic matter in the top 4 inches at either of these sites. I thought more nitrogen would grow more wheat stubble, maybe more cover crop, and leave more biomass behind. It did not seem to affect soil organic matter. So the take home here from these graphs would be, I would recommend selecting covers that produce high biomass over the rotation if you want to build soil organic matter. And by over the rotation, I mean not just the best cover crop biomass producer, but also the best in producing a lot of stubble in the subsequent crop. So maybe a cover that doesn't use a lot of water might actually be better in some cases. So what about other soil health parameters? Here I look at microbial biomass. The fancy term is substrate-induced respiration, or SIR. So I'm plotting this respiration or this microbial biomass on the vertical axis against fallow, that full 8 species mix, and then the single pea cover crop mix. Notice that in general, the cover crops had higher microbial biomass than the fallow, especially at Conrad. But between the two, between the single species and the 8 species, it didn't seem like there was an advantage to having 8 species over 1 species. Any questions on any of that or anything that I've covered so far? Clear as mud? Not clear. Okay. Sometimes cover crops are grown for biomass for use in compost systems. Would you expect similar decrease in performance exhibited by the pea hay systems due to the biomass removal? Yeah, so whether you hay it or you remove it for some sort of compost system, you're still removing that biomass. Notice, you might have seen though, that compared to fallow, a lot of times that pea hay system still did better than fallow. So it's probably better than fallow. It's just maybe not as good as some of the other systems that leave a little bit more residue behind. Okay, so on to wheat yield and protein after a mixed species cover crop. So here, what I'm showing is the 11 different treatments on the horizontal axis, those big 3, the fallow, full, and pea. And then each of these pairs, so a 2 species functional group versus a 6 species without that same functional group. So this is brassica versus no brassica, fibrous versus no fibrous, and fixers versus none, and then taproot versus no taproot. And then I plot wheat yield in bushels per acre for Conrad. Notice that it didn't seem to matter whether we had a fallow or a full or a single species cover crop. In 2019, wheat yield was the same across those big 3 systems. There also was no difference in yield between this 2 species and 6 species mix, this 2 and this 6, but N fixers definitely out yielded non-N fixers, meaning wheat yield after N fixers grew about 4 more bushels per acre, maybe 5, than without N fixers. And taproots, wheat after taproots, for we're not quite sure why, out yielded the 6 species mix after no taproots. So again, though, it doesn't look like there's an advantage to 6 species or 8 species mixes compared to 2 species mixes. Here at Amsterdam, wheat falling fallow out yielded wheat falling the full and pea, but again, there was no difference between wheat yield after that 8 species mix or that single species mix. And the only 2 versus 6 yield difference was that wheat after brassica out yielded wheat after that 6 species mix that did not have brassica. So again, something seems unique with these brassicaceae species like canola and radishes. What about protein? So here we're plotting wheat grade and protein for those same 11 treatments. As you might expect, protein after P was significantly higher, dramatically higher by about 3 units compared to full and fallow. So made a large difference in protein. When we're comparing these 2 species versus 6 species, having a fibrous rooted species or a fibrous rooted functional group actually produced less protein in the falling wheat than not having that fibrous root. And N fixers again produced more protein than not having any N fixers. And this is a pretty dramatic difference. But again, it doesn't look like 6 species did any better than the 2 species, and this 8 species functional group certainly didn't do better than P. Amsterdam, we saw significant differences among all of these 2 species functional groups versus the 6 species. One time, the 2 species did better. 3 times, here, here, and here, the 6 species did better. When we look at what we call the big 3, again, wheat, grain, protein after P, did much better than after full, the 8 species mixer after fallow. So to sum up tonight, cover crops can't compete economically with, say, pea grain or lentil grain, followed by wheat, unless maybe those covers are grazed and produce, animal gain or some benefit that way. It also takes time to change soil quality. In this most recent 8-year study and the 18-year study, we really didn't see many differences after a few rotations. We started to see bigger differences by 6, 7, 8, 10 years in. And higher number of species in mix doesn't consistently improve yield, protein, or soil quality. You might say, well, that sounds like bad news, but I view it as a good result because it allows you, the producer, the crop advisor, the extension agent, some flexibility, meaning you don't have to shoot for a 10 species mix. You can really base your cover crop seed mix on cost, biomass produced, and maybe specific soil health goals. And maybe your best mix is just, for example, 2 species, not 8 or 10 species. To maximize nitrogen and water availability following covers, I strongly recommend early termination, meaning somewhere around first pea bloom, and recommend greater than 50% of your seed mix be legumes. So with that, I give you a big thank you and open up the floor for any questions you have. And please don't run off because Catherine is going to put in a survey here shortly to get some feedback on what I could maybe do differently or better next time around. I got a private question. What is the best way to increase microbial activity? So microbes need carbon. Microbes need plant residue. They need to be fed. And so to me, the best way to increase microbial activity is to feed them. And the best way to feed them is to leave more residue. And so that means, for example, that could be leaving more stubble, meaning not always bailing off stubble. That could mean growing a cover crop and leaving more of that residue, say, rather than haying it off. It likely means recropping rather than crop fallow because recrop generally leaves more residue behind. And so those are the main ways that you can increase microbial activity. Feed the microbes with plant material. Other questions? And do note I have my soil fertility website here at the bottom. I would like you to take a few minutes to evaluate this seminar series by completing a short survey. If you did complete it last week, don't feel like you need to complete it this week unless there was some new revelation or some new idea you had. One thing that we have in there that we'd really like to learn from, whether we, do other remote or virtual sessions, or eventually we'll be going back to in person, is what are the topics that are soil fertility topics that you're most interested in learning about? And so Catherine has added that web link to what's called the Qualtrics survey that just has a few questions. If you could take some time while I wrap up any last minute questions by filling that out, I really appreciate it. Kim, did you see any questions that I maybe missed as I was busy talking?
I didn't see any that you missed, but there is one in there from Jane Upton. Do you see that one?
Yep. Oh yeah, great question. Define greater than 40% legumes and mixtures. So because most legumes are really big seeded, if you did it by weight, you'd end up with not proportional. So I'm basing my numbers, and that Oregon is basing their numbers really on plant stand. And so plant stand is going to really take into account how different species compete with each other, but certainly you wouldn't want to do it on a pound basis, closer to a seed basis. And I would probably look at, standard recommended rates of seeding for, say, pea versus other plants in your mixture, whether those are oats or canola, and try to get at least 40% of your stand of your plants being legumes. I didn't see chemical fertilizer adversely affects soil microbes. Oh yeah, there it is. It ended up between the link um, for the Qualtrics survey and my soil fertility website. So can chemical fertilizer adversely affect soil microbial activity? And so right around April, so fertilizer is salt. Microbes generally don't like salt. I would think and I haven't seen studies, but right around April, microbial activity is probably somewhat negatively impacted, but it would be a pretty small area, and microbes grow back really fast. The more, the more long-term adverse effects would be things like, we know nitrogen fertilizer is causing soil acidification. We know most microbes like the pH to be between about 6 and 8. They don't prefer it being down in the 4s, which we're seeing on some Montana cropland. So that would be a kind of a long-term chemical fertilizer effect. We also have seen here in Bozeman, in that study that I spent quite a bit of time on, that when urea fertilizer was added, it seemed that the microbes that preferred that were kind of what we would call like a weedy species. So urea is easy to use, but then they basically used it instead of breaking down organic material. And so what we found was nitrogen fertilizer negatively affected potentially mineralizable nitrogen. And again, we think it's because the microbes had another source of nitrogen and they didn't need to break down organic matter. So there are some effects certainly, but on the other side, if you don't fertilize, you don't grow lush crops, you don't leave residue behind, and therefore you've taken away the food for the microbes. So there's kind of pros and cons of fertilizer effects on microbial activity. Good question. Should starter fertilizer be used for cover crops to improve stands and microbial counts? Excellent question. We debated this in our study. Should we use a starter fertilizer to give our cover crop a little boost? We thought that a producer would likely be trying to save on costs. They've already spent a fair amount of money on seed that they're not going to get a return on. And so we opted not to. But it was interesting because we fertilized our wheat with nitrogen, and the cover crops the next year always did better in the highly fertilized wheat plot. So there was enough left over that we wish, kind of in retrospect, that we had applied a little bit of nitrogen. I think if you add some starter, a little bit of nitrogen, a little bit of phosphorus, you will see probably a better cover crop, but I would recommend base those fertilizer rates on testing. If you have plenty of nitrogen and phosphorus and potassium and sulfur in your soil, no need to add any extra. If you're really deficient, it's going to give those cover crops a boost. So I would say yes. All right, well, I see the numbers starting to tail off. I will stick around for a few more minutes to make sure all of your questions have been answered. And I also want to say thank you for all those who have attended. I've seen some of the same names. Some of you probably have made it to 5 or 6 or 7, and good job sticking with this. I hope it's been valuable to you, and always feel free to ask me any questions you have on soil fertility. Any final words from you, Kim?
Just wanted to again thank everybody for their participation, and of course all of the extension agents for their collaboration, and then Catherine for always getting us the information out right before the webinar actually happened, so we had a chance to look at that. And then the links in the chat can get you to the different resources, and if you have any other questions, please feel free to contact your local extension agent, and definitely Dr. Jones. And again, round of applause to Dr. Jones for such a great series, and hopefully we can help along the way with more soil webinars coming up, or in-person events maybe coming soon.
All right, thank you, Kim.